Okay, hello Nidir. We'll start with the benzene. Okay, so we'll not cover everything. We'll just cover 25.1 and 25.2 fully, and then this both of these we can discuss next time. Okay, let's get started. Let's talk about a few, yeah, let's talk about a few general things first. So what is benzene? Benzene is like a ring-shaped thing, you know it. So this is what we call cyclohexane. Right before that, like if you want to see, so 1 2 3 4 5 6, so this is called hexane. Right, then you put it in a cycle, call it cyclohexane. But then if you put double bonds on every alternate carbon atom, so now if you now count the number of hydrogen atoms, everyone has one. So here they had two hydrogens, right? But here everyone has single hydrogen. Okay, so this is what we call benzene. Okay, of course. So one thing that you can notice is, so you might say that, okay, why not put it the other way also, right? Yeah, so both of these structures, we'll talk about it a little bit. So both of these are benzene, no problem. In fact, they are the same in a way. We'll talk about, there's something called delocalization of electrons. So that is what happens in benzene. So let's talk a little bit more about that. So what happens is, so every carbon here, if you look at it, so every carbon here, if you look at it, has one sigma, another sigma, and then one pi bond, right? And if you remember how a pi bond looks like is, there is a orbital from C to C, and then you have this on the top, which is a pi bond, and then you have this with good overlap, which is a sigma bond. But here with bad overlap, we said uh, this was the pi bond, right? So here, so in alkenes, if you remember, alkenes, like we had something like, say, this or whatever, right? Uh, say something like this. So these two pi bonds that were there in this one became sites of attack. Attack by whom? By electrophiles, right? Electrophiles are the ones who are positive themselves and seek electrons, right? So they're seeking electrons. Opposite is nucleophiles NN. So they search for negative charges. They are negative charges themselves, so they search for positive charges. Electrophiles, on the other hand, search for negative charges, right? Okay, because they are themselves positively charged. Okay, so this is what was happening. So a similar attack, so to speak, will happen of electrophiles here also, because here if you see that all of them have these pi orbitals, so to speak, and all of them can form this, so to speak, this bond on the top and on the bottom of the ring in a way, right? So you can imagine this like a 3D sort of a thing now. Okay, so if you have something like this, just dismiss that. Yeah, so if you have something like this, then you can imagine that in one configuration here, so in a pi bond configuration, like 1 2 3 4 5 and 6, in one configuration you have bond between this and this, and then in the other you have bond between on the other side, right? Like these are the two configurations that we're talking about. So what happens is, so in that case, So what happens is then this bond will be a little bit longer, and then this, because this bond is a double bond here, so this will be shorter, right? A double bond is shorter than a C single bond C, right? But what we see experimentally is all six bonds of the carbon atom are same, or in benzene are same. So that tells you that there is some kind of a delocalization. So what that means is all of these p orbitals kind of form, like, share with everyone, like like everyone shares with everyone in a way. So we don't know where the double bond is. You can say that it keeps oscillating between the two, like, so maybe this configuration, then this, so it keeps hopping continuously, but the electron, in a way we can say, like, the way I like to visualize it, it's just running around, like, because it can complete the full ring. And that full ring, that concept of delocalization, having a ring, the circle, is very, very important, because that is what gives it the ability to be extra stable. It gives it this ability to have extra special, it makes it special, right? So we just show it by a ring. So that completes our structure of benzene, so to speak, right? So as I said, so bonds are between shorter and longer. They're not too short or they're not too long. We'll see that the number of bond length will be in the middle. We'll see that this is called, the old structure we call it the Kekuli structure. I think he was some French scientist, maybe, I'm not sure. But he thought of the structure as either one side or the other side, but then later he was disproved by saying that the structure is a special structure which is delocalization of electrons. It's not a double bond to the left one or the upper one, but it's just the pi bond is delocalized. That's what we say. Where is the double bond? You can say that it is oscillating between the two in a way, or it is oscillating so fast because you can't even tell whether it's oscillating. Okay, so let's cover your book for a bit. So first, what we see is it is a planar and perfectly symmetrical molecule. So because if this was a single bond, so this would be an sp. This would be a little bit tricky, right? But this is completely flat. That also explained by this. Okay. So then I would recommend that you read the book. It is very nicely written also. So it tells you that the Kekuli structure is incorrect. That's what the main takeaway was. That it's not either left or right, but it is delocalized. Okay, and so as alkenes can go and undergo addition reactions, right? Addition reaction is like hydrogenation, and then they become alkanes, right? But then phenyls, like phenyl, so to speak, is benzenes. Benzenes do not undergo addition reactions easily, because that would destroy that ring that is happening, and that ring really provides it the stability. Okay, so you can see here that the single bond is stronger, double bond is shorter. This one is longer, this one is shorter, and this carbon in benzene is somewhere in the middle of the two, right? Because sometimes it is single when it is in this configuration, when it hops, it becomes a double bond, so it needs to be in the middle somewhere, right? Okay, every carbon is sp2 hybridized, as we talked about. And then we talked about this delocalization. It kind of forms a ring on the top and on the bottom. So this ring is really good for attracting positive charged things, because they can just come and attract themselves to this negative, along a lot of negative charge on the top and the bottom, right? So which is the attack of electrophiles. Okay. We'll take a brief deroute here and talk about the naming a little bit. Okay. So let's talk about nomenclature a little bit. So we call it benzene, of course. So benzene is a ring, right? Now we also call this, when this ring is an attachment. to something, we call it phenyl. Like you remember methyl, right? Methyl was CH3 with attached to something that we used to call methyl. So when a ring can be attached to something, so it will be phenyl. So an example of this will be uh, phenyl. Um, yeah, let me see the book for an example for this one. Yeah, phenylamine. So phenylamine, and another example is phenol, right? Phenol is a good example. So phenylamine or phenol. Let's talk about these two examples. So phenylamine, amine is NH2, so NH2 on the top, right? Phen, all alcohol, so alcohol, right? Okay. Other way is to say that it forms. So benzene directly can, when it is attached to some other things, it can form, say, something like chlorobenzene. Okay, chlorobenzene is simply a benzene with chloro on top, right? Something straightforward as that. So if there are multiple chlorines, one of the examples that a book gives here is 2,4,6 tribromophenol. So let's try to figure it out. 2,4,6 tribromophenol. So start from a phenol, 2,4,6 tribromophenol. So you start from a phenol, right? And then because you start from a phenol, you start counting. So for this is the first carbon on which the phenol is connected, then 2, 3, 4, 5, 6, and then you put 1 on 2. What do you put? A bromo, a 4, and a 6, right? So that's how a nomenclature will happen here. So just to be careful how we are naming. So few of them are named as chlorobenzenes, few of them are named as phenylamine, not aminobenzene, no, phenyl, phenylamine. Okay. And one other example is, we in general we call them aryl compounds, like alkyl compound we used to say. So these are aryl compound, anything which has a phenyl ring in it or a benzene ring in it. Okay, so that's a start. Let's try to look at a few reactions. So in a broad category of reactions, only two three types of reaction happen. So we talked about electrophilic substitution. So we talked about, so the first question in terms of reactions. Okay, we talked about addition, and we said that addition will not happen because uh, because the ring will be disturbed, right? That's clear. Let's talk about substitution now. Substitution, if it is happening, then substitution will be done. What will come first will always be electrophile, so it will always be electrophilic. Why will electrophile come? Because it is itself positively charged and it will want to come towards a negative charge, and benzene ring, as we discussed, has negative charge everywhere, right? And one last thing I think that can happen is hydrogenation here. We talked about that it is difficult to get hydrogenate to uh, to hydrogenate this the usual way, but it can happen. So in hydrogenation in platinum, it will just become cyclohexane. So, but and if there is, say, a methylamine, meth, um, yeah, this is methyl benzene, then it will just become methyl chlorohexane, right? Okay. So these are the two main reactions that will happen, number one and number two. So we'll talk about them. So the second one we have kind of already discussed. The first one has a lot of types, so we'll talk about that slowly. Let me just make sure that is what is happening here. Yeah, that is what is happening here. Okay, and one more thing, oxidation. Let's get oxidation out of the way. Usually, what we talked about, if you remember in oxidation, we said that if there is an alkane you try to oxidize with say KMnO4. If you remember, this KMnO4 is the same region that converted alcohols to acids. Then this would give no reaction, nothing would happen. But what happens here is if you have a benzene ring with a CH3 on the top and you try to oxidize it, because of how benzene is, it encourages this oxidation even though this is an alkane on the top, and this alkane kind of oxidizes back all up to COH because of the benzene ring. So this is what, so it's not the oxidation of the ring itself. The ring itself is stable. That does not, nothing happens to the ring. But what is oxidized is the top part, the alkane part. This is the part that was actually originally not happening, and nothing was happening with it. But because of the benzene ring, something can happen. Okay. So hydrogenation and oxidation is, I hope, clear. We'll talk about the different types of substitution that we can talk about. Okay, so let's look into substitution a little bit. So substitution in a very simple sense is basically, so you have a ring, right? And you have a hydrogen on the top, and say you want to add something, right? Some electrophile, which is itself positively charged. So it will go attack the ring first, and then what it will do is it will put itself there and release an H plus, right? Like it releases that H plus out. So what is happening here is this has gone out and this has come in. Okay, so let's just quickly look at how this happens. Pretty straightforward actually. So there is this thing, and then there is an attacking species right here. It wants an electron. It's seeking electrons. It is one electron short. One pair of electron short. So it needs two electrons. So what it does is it attacks the ring at some point, and it joins there. So what is left there then finally is what we can call a half ring delocalization, so to speak. This is the broken delocalization. Delocalization. So what happens is, right now the electrons can go the whole circle. As soon as this comes and it wants electrons, it takes electrons from one of these things. So it's like, give me two electrons. So what that stops is this motion of the electrons, this smooth motion that was happening before, and now the motion can only happen between these five carbon sites instead of the whole circle. So it is much less stable. And what happens eventually, so right now this one gave electrons to this guy, or we can say that the ring itself gave to this guy, right? And then what will happen is, now for it to restore those two electrons that were given away, now this hydrogen bond can give it back to the ring, and then the hydrogen basically leaves with no electrons. But at the end the ring is restored because the electrons that were given from the ring are given back into the ring, and the hydrogen leaves with nothing. So this is kind of the mechanism. So this, you can say, is the mechanism. Okay, so as a result, what happens is one has gone out and another one has come in, right? Straightforward. Okay, so let's just do quickly a few examples. This is not tricky at all. So there is a ring. If you add NO2 plus, we'll see how this is created. It basically forms NO2 on the top. Simple. If you put a chlorine with AlCl3, so in the first one, the reagent is what we call nitrating mixture. You will see what that is. That is a mixture of HNO3 and HCl. It's a very strong mixture that gives this NO2 plus, and then that can attack. So here this chlorine will react with this, try to form a chlorine plus and an AlCl4 minus, This catalyst kind of takes one in. So this electrophile is created. This electrophile can go attack, as we talked about in the previous reaction. So replaces one here and then leaves with an HCl that that comes out. Right? So one of the hydrogen, one of the Cl plus has gone down and H plus has come out, which is attached to the other Cl here and come out as HCl. Right? Another example of substitution. So let's talk about couple more examples that are mentioned in the book. We'll go over the details a little bit more next time. But we are just talking about it a little bit. So this is what we call uh, Friedel-Crafts reaction. Friedel-Crafts, so we can say first alkylation. So that will, what we'll do is just put a CS3 on the top, right? So the H has gone out here and CS3 has come in. Friedel-Crafts is the name of the two scientists that were working on this. It's a very important reaction, so which is why it's given a name. This is the Friedel-Crafts acylation. So this acyl alkyl, so we understand what it is. Alkyl is a CH3, C2H5, or any other group like that. An R group, right? What we say, right? So, but in acylation, acyl is basically a COR group. So an easy COR group will be COCH3. So let's add that on the top now. So COCH3. So this is acylation. So these groups are called acyls, like these are called alkyls. Again, all of these are same things. So if we start from the start, uh, so this is number 1.1. This is 1.2. Like so, this is we can say we can call it nitration in a way. This we can call it chlorination. But okay, these are not official names, so let's forget about it. But the idea is that here NO2 is getting added, here Cl is getting added, all of this is okay. This is forming phenyl nitrobenzene. This is making chlorobenzene. This is making, so we can call this methyl benzene, or we can also call it, yeah, methyl benzene is good. And then this you can call as acyl benzene maybe. Okay. So we have basically covered the reactions here. There are little details that are not covered. I would recommend that you read the chapter once for that. But the basic mechanism we have covered. So how the Cl plus is created here is also important. But at least I have not covered that. These are the Friedel-Crafts reactions. So in which so this is alkylation and acylation. So ethyl benzene. So we have created this. So this comes in. So just we'll go through the details once a little bit. Let me just go through it from the very start a little bit slowly so that if you want to pause the video and you want to look, you can. The first one is electronic substitution with chlorine or bromine. So that just adds a bromine. So for that, what you need is a bromine plus that is created through this Al, the catalyst reaction. This is a temporary thing. This Br plus needs electrons, so one of the carbons will give it, breaking the delocalization. Then the delocalization is resumed in stage 2 when this bond is broken back and H plus leaves with no charge, and the two electrons are given back to the ring to make the ring go again. Okay, so this is one thing. Okay, another thing is they said that if you keep adding bromine here, so the first bromine gets added on the top, the next bromine will not get added. So let's talk about this a little bit. So okay, so there is something called activation and deactivation. Okay, so what that means is, so if there is already a bromine here, okay, and that we say is an electron. Hold on, my Jamboard has crashed. Yeah. So if say this group, we are talking about activation now. So if activation with the electron donating group is there, then what that does is it activates uh, 2 and 4 site, 2, 4, 6 site. So what that means is, so this is the first carbon, this is the second, third, fourth, fifth, sixth. So that activates this site, and this site. Whenever more Br2 will be added, will be substituted. Then first one will be substituted here. The second one will be substituted. Okay, so maybe Br is not a good example, so, but maybe let's talk about something like a CH3 here, which is also electron donating. So if there is a CH3 here, and then you are adding Br now you are substituting in. So you'll be adding more Brs like this. So something like this. So not on this carbon and this carbon. So because those sites are deactivated. But on the other hand, if you have something like an electron withdrawing group, something like an NH3, NH2, or a COOH, something like which is electron withdrawing, then that deactivates site 2, 4, and 6. So exactly opposite will happen if you add Br here. If you try to substitute it out, so NH2 is there, and so it will try to add itself to like these two sites instead. Okay, so this is a very important point that they mentioned about activation and deactivation. Okay, so this is what they're talking about, that if you try to add more chlorine or bromine, as in our case, you get added to 2 and 4. So 2-chloromethylbenzene or 4-chloromethylbenzene. Okay, feel free to pause the video at any point to see whatever you have to. Okay. Uh, yeah, this UV ultraviolet thing, if you remember, that would UV used to add chlorines everywhere, right? So that does not happen with the benzene ring. It'll substitute on other sites. So if you keep doing it, all the H's on the methyl will get replaced, not these ones. Okay. We talked about nitration. So nitrating mixture is HNO3 and H2SO4, not HCl. So it makes this NO2 plus. That is the important one. The rest everything you can forget. But this NO2 is important, and that's what comes and attacks with the same reaction as we discussed. And I talked about how NO2 is a bad agent, so it is an electron withdrawing thing, which also includes COH and NH2 also, all three. So they all will deactivate those sites. Okay, and then we talked about Friedel-Crafts. Friedel-Crafts reactions are basically alkylation or acylation of benzene. Right, alkylation means the addition of CH3 and C2H5. And acylation means COCH3 or COC2H5. Right, and the mechanism is exactly the same as we discussed. Right, you have AlCl3, so Cl will get pulled away. This will form a plus. This plus is ready to attack. Here, in this case, Cl will get taken away. Here, COCl3 is plus. That's ready to attack. So just to be clear here, so this Cl goes away. This forms a plus, and this plus now is going to attack and forming this, breaking the chain, and then this H breaks, and then the chain is restored. Similarly, in acylation, this bond breaks, and similar mechanism. Okay, but as we talked about oxidation, oxidation is only in the side chains. So arenes is also another example, another name for benzene. When we try to oxidize it, it only oxidizes the side chain, not the main one, as we talked about. So this one will get oxidized to COH. This does not happen under normal conditions, but because of benzene, it is possible to happen. Okay, and finally we talk about hydrogenation, where all of the rings is destroyed and it just becomes cyclohexane or cyclomethylbenzene or something like that, right? Just straightforward. Okay, we'll stop here. We'll continue with phenol next time. So phenol is a special type of benzene, so to speak. Benzene with an attachment with of OH. and this is so important that it's used a lot in a lot of places. You will see a lot of special properties of phenols, but the broad idea about benzene we have covered. Just keep rewatching the video a couple of times. I think you'll get. Okay, bye bye.